Hi, my name's Ginelle and I'm going to be doing a project on the manufacture of sulfuric acid. So, as we covered synthesis reactions in class and in the textbook in section 4.2, my presentation on the manufacture of sulfuric acid will illustrate the use of synthesis reactions in daily life or in industry. As well, since in the textbook I also mentioned the manufacture of sulfuric acid, I will be elaborating on the summary given. Sulfuric acid is one of the world's most important acids and is used in almost every industry as a drying agent, an ingredient, or a catalyst. It is found in fertilizers, cleaning products, plastics, cars, batteries, and many other commonly used projects. Considering its many uses, it's no surprise that in the US, more sulfuric acid is manufactured annually than any other chemical. So for example, 704,000 metric tons were produced in the US in December 2010 alone, and in Canada 2008 saw 4.5 megatons of acid. Due to its heavy industrial use, the consumption rate of sulfuric acid is regarded as an accurate indicator of a nation's industrial development. Therefore, the study of its properties and the production thereof is of great importance. So, sulfuric acid is a viscous, colorless, odorless, and oily liquid. It is a very strong acid which is virtually 100% ionized in solution, meaning that if you put the acid in water, all of the hydrogen atoms break away from the SO2 group. It is hygroscopic, being able to attract and hold water molecules from its environment, and is also water-soluble. It is usually around the pH level of 1 and is extremely corrosive, causing severe burns when in contact with skin and can melt through paper and fabric. It is not recommended to inhale or ingest as it would be very painful. So there are two main processes of producing sulfuric acid, the lead chamber process and the contact process. In both processes, sulfur, iron sulfide, or hydrogen sulfide are burned to produce sulfur dioxide. After that point, the process is split. First, I will talk about the lead chamber process. Okay, so of the two processes, the lead chamber process is older and less costly but can only produce sulfuric acid ranging from the concentrations of 62 to 78%. It was developed in 1746 by John Roebuck and it was the first method of producing sulfuric acid by the ton as opposed to only a few bottles at a time. Okay, so first, the sulfur dioxide gas is released into this chamber called a Glover tower, where it is mixed with nitrous vitriol and water. Now, nitrous vitriol, for those who don't know, is sulfuric acid with nitrogen oxide and nitrogen dioxide mixed into it. Sulfur dioxide is oxidized into sulfur trioxide at this point and then is dissolved into the acid to create what is called Glover acid, which is approximately 78% sulfuric acid, and that's collected at the bottom of that chamber. The remaining gases, which contain sulfur dioxide, some sulfur trioxide, nitrogen oxide, nitrogen, and oxygen, are then passed through into another chamber, a lead-lined chamber. And in this chamber, only one lead chamber in this diagram, but in some plants, the gas can go through from 3 to 12 numbers of these chambers, and the acid produced in each chamber would be collected at the bottom of each of the chambers. After the gases have gone through a number of these chambers, the rest of it goes into this tower, which is called the Gay-Lussac tower, where it is washed in the Glover acid. So from this, it gets washed with the acid over there. And this actually creates the nitrous vitriol acid, which is used in the Glover tower. The waste gases are then put into the atmosphere. Yeah. Okay, so the following reactions occur. Nitric oxide reacts with oxygen to form nitrogen dioxide. Nitrogen dioxide reacts with water to form nitrous acid and nitric acid. Sulfur dioxide reacts with nitric acid to form nitrous sulfuric acid. Nitrous sulfuric acid reacts with nitrous acid to form sulfuric acid, nitrogen dioxide, and nitric oxide. Sulfur dioxide reacts with nitrous acid to produce sulfuric acid and nitric oxide. And overall, the nitrogen oxides act as a catalyst to form sulfur to make the reaction sulfur dioxide reacts with water and oxygen to form sulfuric acid. So the concentration of this acid is always less than 80%, which means it has very limited uses. Most of it goes to the production of fertilizers. All of the new plants now use the contact process, and all of the plants in the USA use the contact process as opposed to this one. So now I'll talk about the contact process. The contact process can produce sulfuric acid at any concentration, but requires pure raw materials and therefore is more costly than the lead chamber process. In this process, purified sulfur dioxide is heated to 450 degrees Celsius, and then using a catalyst, usually vanadium pentaoxide with an alkaline metal sulfate, is reacted with oxygen to produce sulfur trioxide. The sulfur trioxide then enters the absorption tower, where it is absorbed by concentrated sulfuric acid to create oleum, and then is reacted with water to create sulfuric acid. The end product is 98% sulfuric acid, which can be diluted to the desired concentration. Waste gas is released into the air, but to limit the amount of sulfur dioxide being lost, the gas once again undergoes another round of the contact process before finally being set into the atmosphere. Overall, the following reactions occur. The combustion of sulfur, which is sulfur reacting with oxygen to form sulfur dioxide. The catalytic oxidation, which is sulfur dioxide reacting with oxygen to form sulfur trioxide. Sulfur trioxide absorption, which is sulfur trioxide reacting with sulfuric acid to form oleum. And the dilution of oleum, which is oleum reacting with water to form sulfuric acid. Sulfuric acid can be found in almost any area of our lives. It is used in the manufacturing of fertilizers, phosphoric and hydrofluoric acid, soaps, detergents, food additives, organic chemicals, explosives, plastics, rubber, and batteries. It is also used in petroleum refining, electroplating, uranium ore processing, and the pulp and paper industry. In Canada, the largest consumer of the product is the mining and smelting industry. So, though sulfuric acid has many uses, the gas emissions released as a byproduct of production is quite harmful. The released sulfur dioxide and nitrogen oxides are converted to sulfuric and nitric acid accordingly in the air and then fall back to the earth as wet sulfate or nitrate deposition. These chemicals combine with moisture to form acid rain, which falls back to the earth to kill bacteria, plants, and fish by decreasing pH levels in their aquatic environment to intolerable levels, also known as acidification. And this acid rain also damages sensitive oils and trees of high elevation. As well, it accelerates the decay of city buildings and destroys statues, sculptures, and stone monuments. It is recorded that in 2003, Canada released 2.4 million tons of sulfuric acid. Between 1994 and 2003, Ontario emissions alone made up 52% of that total. Fortunately, actions have been taken to reduce these emissions. In 1997, in response to the acid rain assessment pointing out the need for further decrease of sulfuric dioxide emissions, the Canada-wide acid rain plan for post-2000 was developed. It aimed to reduce sulfur dioxide emissions nationwide, giving target goals for each province. As a result, in 2006, Canada's total SO2 emissions were 1.7 million tons, 47% below the national cap of 3.2 million tons. In 2008, Canada decreased its sulfur dioxide emissions by 96% of 1970 levels. Even now, Canada continues its strategy to reduce sulfur dioxide emissions. So, sulfuric acid benefits society in many ways, though mostly through the products it creates. It makes water-soluble phosphates, which is essential for plant growth. It is a major ingredient in car batteries, and its strong affinity with water makes it an invaluable drying agent for various industries, such as the pulp and paper. It is when mixed with water, a highly exothermic reaction occurs, and the energy released can be enough to heat the mixture to boiling, but it does not come without risk. Workers in the lead battery industries have reported teeth erosion only after 4 months of exposure to the chemicals. Finally, byproducts of sulfuric acid production contributes heavily to Canada's acid rain problem. But despite the risk and problems, sulfuric acid continues to be an essential part of society. There is not one place one could go in a city that sulfuric acid has not had an effect on.